Okay, ready to start? We are moving on to a different topic today.
I don't want your feelings,
It's called optimization. So we pretty much learned everything we're going to need for curve sketching. We kind of don't want to waste time doing more examples, applying the same idea. So we're moving on to another application of derivatives, optimization. So besides linear approximation, this is one of the most prevalent uses of calculus, although there are situations in which calculus cannot be used for optimization, but those aren't the situations we care about. We care about pretty much using calculus to design the best possible scenario. Given some constraints or restrictions. It's the same here. I might use either word. So that's what calculus is about. It turns out that often best can be interpreted as maximum or minimum. And we know, hey, derivatives help us find maximums and minimums. And so this now, whenever you're in a situation where finding a maximum or a minimum is what you want to do, calculus is one of the first things you probably should think about. So pretty much you're in some sort of situation where you do have restrictions, constraints, limited resources, etc., that you need to get something done within that context, and you want to make it as best as it can possibly be, the best possible scenario. And oftentimes you can describe that in one of these two ways. So if you are, for example, you might want to maximize profit, minimize cost, or do something like that. But a lot of times, what is the best thing that can happen? Usually you can phrase that in terms of we want a lot of this thing and not a lot of that thing, right? And so finding maximums and minimums are kind of tied into this whole thing. So that, of course, once it comes to maximums and minimums, we know that the first derivative is going to be a very useful tool in general, and optimization is just describing the process by which we can use calculus to actually get this done. So again, this is a handout. So I'm sure you have a handout, you're reading the handout. And there are things that I'll gloss over that you should probably read in here in detail. But yeah, that's the basic idea. It is much like related rates and curve sketching. It has its own sequence of steps. So again, optimization shouldn't really be a problem that you get stuck on. You should always know what you should be doing first, second, and third, and etc. And so what I like to do with this kind of problem is I like to actually illustrate the steps. Well, I'm always going to be pointing out the steps, but before actually reading through them, I actually like to actually go through an example while illustrating the steps. So I'm going to actually do problem 1 in the handout, which is on the second page. And while we're going through problem 1, I'll illustrate for you the steps. So, turns out just like with related rates and many other things, the first step is to read or make sure you understand the situation that you want to optimize. So we're going to read the problem. So problem 1, a farmer has 100 feet of fencing. He wishes to make a rectangular enclosure. If he wants the enclosure to encompass the maximum possible area, so that he can plant the maximum number of crops, what should the dimensions of the enclosure be? So first thing you have to understand here is that, okay, we know what the goal is. We want to build a rectangular fence. Now there are tons of ways we can build a rectangular fence. However, there is some constraint here in the problem, as you can see. the farmer only has 100 feet of fencing. So pretty much he has the restriction that he only has 100 feet of fencing to make this rectangular fence. And so you might wonder, what would be the best possible rectangular fence that he can build, right? There are many examples of rectangular fences that he can build. He could make it a 10 by 10 by a 10 by 40, right? That's a way to build a rectangular fence where he has 100 feet of fencing. You could do something like 25, 25, 25, 25. That's another way to build a rectangular fence. You could do 30, 30, and 20, right? There are many options here, right? So he wants to find the best option, the option that's going to get him the maximum area, right? So for this farmer, there is such a thing as the best case scenario. He's a farmer, he wants to be able to plant a lot of crops, and so he wants to build an enclosure to do that, but he has the constraint of the fact that he only has 100 feet of fencing to do it. Okay. So the second thing is, much like related rates, it's often helpful to draw a diagram. Situation, if possible, if necessary. And again, we're going to label things intelligently. So that would bring us to the second step. Obviously here, our diagram is going to be a rectangle. Now we are going to label it, of course, using variables to represent our unknowns. So all we know is that this guy wants a rectangle. We have no idea what the dimensions or should be, at least not in the beginning. So we could label them as x and y. So let the length of the fence be x, let the width be y, and that's the diagram in my situation. And somehow I want to make this combination of x and y to be the best possible scenario for this farmer. Okay. So now we move on to step 3. Now step 3 is an important step. And just like in related rates, it is often going to depend on that picture you draw. But different from related rates is that rather than coming up with one equation to describe the situation, you'll actually need to be able to describe it with 2 equations. So you are going to find what you call your objective equation. Oh, let's find constraint. Your constraint equation. And you are going to find what's called the objective equation. So you actually need 2 sets of equations for this process. Now, what your constraint, what equations, what's the point of these equations is that they serve 2 very different purposes. The constraint equation describes the restriction that we have. And one key way to know the restriction that you have, it's usually going to be something that you're given. You have no control over it. Someone's going to tell you, okay, this is the resources that we have, right? So you're going to be told about some restriction. The objective equation is going to describe what you want to maximize and minimize. So you want to get the best possible scenario in a very restricted context. You are going to talk about your restriction in terms of an equation. We call this the constraint equation. And you're going to talk about the thing you want to make as large or as small as possible. And that is talking about what we call the objective equation. So here, what is our constraint in this situation?
Perimeter has to equal 100.
what? The perimeter. The perimeter is our restriction, right? The distance around this thing has to sum up to 100. So our constraint here is perimeter. So I need to be able to come up with an equation that's going to describe the perimeter. And I'm going to need to come up with an equation such that it tells me about the restriction of the perimeter. And so the perimeter is, of course, computed by adding up all the sides. So that's 2x plus 2y. And that must be 100. So that equation describes my restriction. Of course, I can simplify this a little bit. I can say the x plus y must be equal to 50. Okay, so this equation, of course, is based on the labeling of my diagram, describes the restriction that I have. And we call this the constraint equation. And what is the objective supposed to describe here?
Area.
Area. So in this situation, the area is what we want to maximize or minimize. That's what the problem says. He wants to make sure it encloses the maximum possible area. So therefore, I'm going to come up with an equation that would describe the area. Now the thing is, a priori, we don't know what the max area is, so that has to be just a variable. But we do know in terms of our diagram how we would compute area. It would be, of course, x times y. This is called the objective equation. So you have a scenario that you want to optimize, meaning you want to make it as good as it can possibly get within a certain restriction. Oftentimes this means maximizing or minimizing something, so you can go through this process. Make sure you understand the situation, draw a diagram, it might be helpful, and then come up with equations that would describe the restriction and the thing you want to make as good as possible. So in this case, it was perimeter and area, respectively. Okay, so now we move on to the next step. Now there are contexts in which we'll have to deal with guys like this, but that is multivariable calculus. You'll notice that this equation is the one we really care about, but it has two variables in it. We are in calculus 1, we don't know how to do calculus with two variables. We need to get it to one variable. That leads to step 4. We need to describe what we want to fix in one variable. So step 4 is always going to be solve for variable in the constraint and plug its expression into the objective. So this guy's in two variables. That is very inconvenient for a Calculus 1 student. However, I know a relationship between those two variables from the constraint equation. Therefore, I can get this objective into one variable. So, since x plus y equals 50, I can solve for one of these variables. In general, it doesn't really matter who you would solve for, but there are some situations in which solving for one might be easier than the other. Here, it doesn't really matter. So I'm going to solve for x, 50 minus y. So this means that I would be able to describe my area in a single variable by simply replacing the x with 50 minus y. And this will make my area. I can describe the area equation as this equation. So now I have my objective in one variable. Now remember, this is the thing that we care about. We care about the area. We want to make this as large as possible, and that leads us to step 5. We will maximize or minimize this objective based on, of course, what you want. In this case, of course, we want to maximize it. But as a general step, it could be either or. So here we want to maximize or minimize this new objective. Now I'll mention here, and it's actually written down, that technically in general, what you should be looking for is the absolute maximum and minimum of this new objective. But it turns out the extreme case of being on the boundary is usually not going to be the solution. That's not always true. There are rare cases where it is, but usually it's not going to be. You don't have to worry about that. To go to one extreme or the other here, the smallest possible value for x is 0, and that would be the largest possible value for y would be 100, and you can do vice versa. But obviously in either of those cases, you don't have a rectangular enclosure. So those would be the endpoints technically. X can range from 0 to 100, and so can y range from 0 to 100. But picking at the endpoints would obviously not give you a solution here, not a viable one anyway, right? So the endpoints we'd ignore it in this case, but in general you should consider them. Right? So it turns out that in this case, the maximum that we want is going to be a local maximum. So how do we find local maximums?
So the derivative equals 0.
Right, you find, essentially it's the first derivative test is what we're going to do here. So we're going to find a prime, which is going to be 50 minus 2y, and we're going to set it equal to 0 or undefined, and we're doing this for the critical points. Obviously, this is a polynomial, it's never undefined. So setting it equal to 0, we can solve for y. Turns out y would be 25. Another parenthetical statement here is that usually if I give you a problem and there's only one answer that you can find, that's the answer you want. In general though, you might have several answers here and you would have to test them. So just to remind you how you would actually test this, you would put it on that interval. Right? So you plot 25, minimum was 0 or 100, and I would plug in numbers in between. So I plug in 1, let's say, and I plug in 26 into the derivative. Now if I plug in 1 for y, I get 50 minus 2, that is clearly positive. If I plug in 26 for y, I would get 50 minus 52, that is clearly negative. So it turns out that this would go up and then down, and therefore that would make this one a maximum. So it turns out that is the value that we want. So it turns out to make the area as large as possible, we need the y value to be 25. Now, this leads us to step 6. Oh, yes, step 6. And this is to answer what is asked of. So now let's go back to the problem and make sure that we can give the answer that we want. It says, what should the dimensions be? Which means a full answer to this problem, I would have to tell you the dimensions of the rectangle. I need to tell you what should the length and width of this rectangle be in order to achieve the goal, right? There are times when they could have asked for something else. They could have asked for, hey, what would be the maximum area? In which case you don't necessarily care about the length and the width, you just care about the a value, and you could, at this point, you could just take that 25, plug in here, and that would be your answer. So you have to make sure that you look for what is required, and you make sure you give your answer to talk about that. So in this case, we need to talk about the dimensions. This means you need to say length is equal to, and width is equal to, or you can say something like in like a length by width kind of phrase. So since we need both the length and the width, it also means I need the x value here. And so knowing that I need the x value, I would simply go back here. So again, I wouldn't always compute the x value, it depends on what I'm looking for. In this case, I need the dimension, so I need both values. So here I would say, okay, I know that my x is 50 minus y, And if my y is 25, that means my x is also 25. So it turns out that a square is the best possible rectangle for this scenario. So it needs to be 25 feet and by 25 feet. That would be your answer. Or you can write something like 25 by 25 for enclosure. And that would be your answer, right? But make sure that you answer what is specifically required of you. So you can't stop here and just say y equals this. That's not what you were asked for. Or you can't just say, oh, the maximum area would be this, 50 times 25 minus 25 squared. That would not be the answer that you're looking for. Here they ask for the dimensions, so you respond with the dimensions. And that's it. That defines the procedure for optimization. And that will be the procedure for every single optimization problem. Any questions on this run through? So again, make sure you read this in detail for any little hiccups. And you would of course need to know these steps. Eventually, you should read through them in detail to make sure you understand why each step is necessary. But after that, just remembering the bullet points as a quick, like a memory peg here, should be good enough. And if there are no questions, we'll just finish the session by doing some more examples to make sure that we know how to do this. Okay, so let's run through problem 2, and maybe you guys can now give me some feedback. Oh, by the way, there was a non-calculus way to do this. Did you guys notice that? What would you do if you weren't in calculus class? Meaning step 5 you wouldn't have done. Could you have figured out the answer some other way? You didn't jump out of it. Because the area is that guy. What do you know about that guy?
It's a perfect square. It's a difference of squares.
A difference of squares? Well, not really, not without a...
Well, you could factor it, right?
Sure. And to what end? What kind of equation is it? What kind of object is that?
It's a,
Huh? If you were to draw a picture of it, what would it look like? It would be a parabola. Okay? What kind of parabola? This one?
no,
Or
it's
this
down.
one? You notice that if you were to draw this, because the square term is negative, the picture would look like that. And of course, to find the maximum of a parabola that looks like that, you would go after the vertex, right? And so we could actually find the maximum point here by just looking for the vertex of this parabola. And what is the vertex? It's the formula for the vertex of the parabola.
Negative b over 2a.
Minus b over 2a. Your y would need to be minus b over 2a to find the vertex. In this case, your b is 50. It's minus 50 divided by 2 times the a is minus 1. And you notice that you have gotten 25 as well. So there's a non-calculus solution to this one. Even though we used calculus, that was kind of overkill. Of course, the issue comes in if your function is not a parabola, right? Because there's no general formula to find maximums and minimums of arbitrary curves, right? That's why you need calculus, right? There's no vertex formula for a random cubic. Okay? So in this case, technically didn't really need it. It's just an easy example to show you guys the ropes. But yeah, you can understand that if you can find the maximum some other way, then it's doable that way. But if you're required to use calculus, or you have to use calculus, or you're in a situation where you kind of have no choice, this would be the process. And of course, like I said, there are other cases in which calculus itself is not going to be viable. Maybe because the derivative doesn't exist, or whatever reason, you need to find the maximum some other way. But you do need to understand the problem, be able to maybe sketch it out to see what's going on, and then actually maximize or minimize. Let's actually do example 2. Okay. Design an open rectangular box with square ends on the left and the right side, having a volume of 36 cubic inches. That minimizes the amount of materials needed for construction, because we like to save the earth. One is we read to understand the situation. Of course, I want to design a box, so that means I'm going to tell you what is the length and width needed to make that design. I also know that the box is to have square ends. So that will give me a clue of when I'm starting to draw my diagram. It's going to be a box. It's supposed to be open, so it does not have a top. Okay, so that is my box. Now, I want to design this box, so I'm going to start labeling the pieces. What do you want to call the length and the width? Doesn't matter.
L and W.
Want to call it L and W? So L, W, what will be the height?
Has to be L, or it has to be the same as one of them.
Yeah, well, let's this is the left. Let's say this is the left and right side. This is the front and back. So what would it be here? This is left and that's right. Right is facing this. What will be the height in that case? So this is the front. This side is the right side. Now it doesn't matter. I just randomly picked which one I wanted it to be. But once you pick, how do you continue the labeling?
It would be W, because the left and right.
It would be
are
W. So this is what I mean label intelligently. You do not want to use 3 variables here, because that's going to get you in trouble down the road. It told us that it has its square ends on the left and the right side. So I picked a side that I just chose to be the right side because that's how I oriented it in my head. And okay, so that means I want this to be a square, which means its length and its height must be the same value. So that's my diagram for the situation. Now 3, I want to talk about my constraint equation and my objective equation. What's the constraint here?
Volume.
Volume, right? So the constraint is going to be usually the given thing. They told you volume is 36, right? You have no choice over the volume. That's the situation you're in. That's how much space you're allowed. So we know that volume is the constraint here. And based on this diagram, how would you talk about volume?
LW squared.
Right. Length times width times height. And so now we know that LW squared must be 36. So that is my constraint equation. What is the objective here?
Surface area.
Surface area. It says we want to minimize the amount of material used. For a given thickness, minimizing the area will give us that. And so how would I talk about the area here?
LW plus 2W squared.
3LW, explain your reason.
Well, surface area is typically 2LW plus 2LH plus 2WH, and here width equals height, so you can first replace all the H's with W's, and then where you don't have a top, so there's one missing side.
Yeah, so, I mean, you walk around with that formula just memorized. Yeah. Well, yeah, but you can have, you can just look at your picture and just realize that I just want the area of all the faces of whatever this thing is. The faces are all rectangles, right? And so, okay, what is the area of this one? W squared. The area of that one is also going to be W squared. So that's 2W squared, and that's for the right and left.
Oh my God.
Plus, I can tell you a shape where you're not going to have a formula memorized for it. Okay, so you should know how to look at your diagram and pick out the pieces.
Well, I could have done that too, but I just figured that was an easier explanation.
Huh?
Nothing.
It's easier explanation if you just have these formulas in your mind all the time, which I guess it's fine. But I don't really like memorizing things, so like I like to know how to, once I set it up, just to make sure I can construct the answer. So, right, you add the left and the right side, that's W squares. Notice that the front is L times W, the back is also L times W, and the base is also L times W. That's where the 3LW came from. And so this is for the front, back, and base. So, in other words, I have here the constraint is LW squared equals 36, and the objective is going to be A equals 2W squared plus 3LW. So now this brings us to the next part, which is to what?
Solve for what variables.
Right. Now remember, the objective is the guy you care about, right? So he has several variables, so what you always do is you go over here, you solve for one of the variables, and plug into the objective. So who do you want to solve for here?
You want to solve for L.
Probably solve for L. Why? Because if I solve for W, it's going to give me a radical.
L, yeah.
Right. So again, in general, you can solve for any one you want, but you tend to want to solve for the easier one. Solve for W would involve me having to deal with a square root, so I'm going to solve for L. So I know that L is equal to 36 over W squared, and that would mean that I'm just going to go over here and replace the L with that. And so this, you cancel that. And so this is 2W squared plus, what's 3 times 36?
108.
So we have that guy. Now, I also don't like arithmetic, so if you guys are all here, I might as well just ask you. So, now we're immediately in a situation where you probably don't know a general formula to find the vertex or max or min of this guy, and so that's why we're going to use calculus. Unless you know a formula to find the maximum of this?
If you did, Javon, I wouldn't even tell you.
So you just want, oh, you just use this formula? Okay. So here we wouldn't know ahead of time a formula for that, so that's where the calculus is going to come in. We need to now, in this case we have pretty much the opposite kind of objective. We want to minimize this guy. But it's going to be the same, essentially the same procedure. We're going to be doing the first derivative test. So we are going to find the derivative. This is going to be 4w minus 1/8 over w squared. And we are going to want to solve that. So we're going to set this equal to 0 or undefined. And that's for critical points. Now, a quick check can tell you that for this to be undefined, my w would have to be 0. If my w is 0, I don't have a box. So I'm not going to care about that critical point anyway, right? It's not going to be where the answer is. And so I really care about where this is actually 0. So this would mean I have 4w equals 108 over w squared. This means that w cubed is equal to 108 over 4. Does that go in, is that something nice? What's 4 into 108?
27.
7. And so my w is going to be 3. That brings us to step 6. For step 6, to talk about the design of this box that I just made, I need to be able to tell you my L and W. So if W is going to be 3, I can solve for L here. L must be 36 divided by W squared. So this is going to be 36 divided by 9, which is what?
4.
4. And so here I can now answer the question. Box should be a 4 by 3 by 3 meters or inches. And that's your answer. Obviously this tells you about the square side. Should be a 3 by 3 inch box, and the other length dimension should be 4. So of all the possible boxes that we could create, that's the best one if you want to minimize the surface area. Right? Other than not building a box at all, that's the best one. So are we understanding the process here? And yeah, again, it's kind of like related rates. It's like 1, 2, 3, 4, 5, 6. Like it's always these 6 steps. So just make sure you would generally do them in this order, because at every step you use the previous step to kind of figure it out. So in general, you should go in this order exactly to solve these problems. It'd be nice if you label the sections as you're going through them. It'll make it easier for me to grade, but you don't have to technically. Just you should know in your head what you're doing first, what you're doing second, what you're doing third. And once you get to the 6th step, you should be able to answer the problem. Okay. I know how many more examples we can do, but let's maybe turn to problem 4. Kind of interesting. It's not really rectangular like the first 3 examples. It's cylindrical. Okay, so let's jump to problem 4. Let's kind of do this same idea. And of course, you should go through the other examples to make sure you know how to deal with them. Okay. Okay, so let's read. A cylindrical can without a top is to be made to hold 8,000 cubic meters of liquid. Don't know why we call that a can, it should be more like a tank. Find the dimensions of the can, which will minimize the amount of material needed to make the can. And again, that is, you want to minimize the surface area. Okay, so our diagram here is going to be a can, cylindrical. Where, again, there's an open top. We can start to label here. Let's talk about the radius of a can and the height of the can. These are unknown, but we do have a constraint, and the constraint is, again, here, volume.
Thank you.
We know it is volume because it says that's how much the can holds. We also know it's volume because it mentions cubic units. So cubic units means volume, square units would mean area, etc. So sometimes the units themselves can indicate to you what kind of quantity you're looking for. So volume is our constraint. They told us specifically that the volume has to be 8,000 pi. But what is the formula for the volume of a can?
Under pi squared h. No, that's not.
Just pi squared.
Pi squared.
Just gonna make Julia the formula girl anytime I need a formula. Hey, let's
Did I not just require, you made fun of me last time, so I said it underneath my breath. You heard it, right? You have to be nice if you want to participate.
Okay, what's the objective here? Oh, well, we already know. So what's the area? How would you find the area here? Surface area.
Two pi RH plus pi r squared.
Why 2 pi RH?
I don't know. I know that you have to like do the sides and the top, but
Yeah.
so it's definitely
Yeah,
pi r
so
squared
the
H.
idea with a can, this strategy is you kind of slice it, and then you unfold it. And so you're really looking at some rectangular piece that we folded in a roll and the circular base, right? Now, of course, the length of this rectangular piece is going to be the circumference of the circle, because that's what wrapped around. And so that's 2 pi r. And then this is the height. And then you have one disk of radius r. So then that gives you the area is going to be pi r squared plus 2 pi r h. And if there was a top, you would have 2 of these disks, and so you would have 2 pi r squared plus 1 h. But here there is no top, so that's our formula. Now, we're going to do step 4. We're going to solve for one variable in the constraint. We're going to plug that into the objective. For the same reason, I'd rather solve for the h than the r, because to get the r, I'm going to have to get rid of that square. It's going to cause a radical. So solving for h, we see that h is the same as 8,000 over r squared. And so this means that we can express the area by just replacing this expression for h in the area formula. It's going to be pi r squared plus 2 pi r times h. So that's our new area formula in one variable, the variable r. So now we want to minimize this. So we're going to jump in, finding its critical points, finding the, so this is 2 pi r minus 16,000 pi over r squared. Set is equal to 0 or undefined for critical points. Of course, we're going to ignore the undefined. It's undefined when r is 0. If r is 0, we don't have an object to begin with. So we will simply set this equal to 0. And so I can divide both sides by 2 pi first. And multiply it through by r squared, we get r cubed minus 8,000 equals 0. So I will get r equals the cube root of 8,000. And that will be 20.
Yeah.
So r is 20. Find the dimensions. So the dimensions of this guy is going to be the radius and the height. So this would imply that the height is actually 8,000 divided by 20 squared. That's 8,000 divided by 400. So that's also 20. And so those are the dimensions. Radius is 20, and the height is also 20. That will help us to construct an object like this that will hold 8,000 pi cubic meters of stuff, and it will also have the minimum possible area. Okay, so I guess we'll stop there. Again, try the other problems, make sure that you can get your practice on actually constructing these things. Of course, step 2 and step 3 are really the main parts of these problems. You should be able to draw a picture, label it accurately, and then use that picture to come up with some equations. And after there, it's kind of follow your nose, but so you should get a lot of practice on setting up step 2 and 3.